So everything I'm going to be talking about today was done under the umbrella of the SAGES collaboration. And this is a reasonably up-to-date list of my SAGES collaborators. And the local UCSC collaborators are shown in yellow, like banana slugs. And I'm going to give you a bit of background about globular clusters and why they're so great for unraveling the star formation and assembly histories of galaxies. Basically because virtually all galaxies have a retinue of globular clusters. The globular clusters, the premise is that the globular cluster formation accompanies all the major star-forming episodes in a galaxy's history. And once you've formed the globular clusters early in the history of the universe, they remain as unchanging bright beacons that basically are along for the ride. They accompany and witness all the mergers and acquisitions that go on through cosmic time to build the galaxies we see today. Because they're bright fossils, we can do spectroscopy, detailed spectroscopy of a significant sample of the globular clusters around any given galaxy, out to about 50 megaparsecs or so. And from those spectra, we can get not just the kinematics of the globular cluster system, but we can also get the chemical element abundances. And so with these traces, we can really start to say something interesting about the formation histories of the galaxies. So I'd like to just point out this landmark paper that we all remember from 1978, where Searle and Zinn actually used the combination of the kinematics and the chemical element abundances together to deduce the accretion origin of the Milky Way halo, basically the two-phase origin, the inside-out build-up of the Milky Way. So that leads me to my theme. One of the themes of this talk is to use globular clusters and galaxy starlight to test this two-phase paradigm of galaxy formation. And I don't really have to explain this paradigm to this audience. We are all familiar with the idea of forming a nugget at relatively high redshift and growing that nugget over time by the continuous raining in of smaller objects, of satellites that build up the galaxy. And of course, the expectation is that the more massive the galaxy, this is log mass over a half-light radius, the larger the galaxy, the more massive the galaxy, the greater the proportion of accreted material. So we're going to use the globular clusters and the starlight together to try and address some of these questions. Which galaxy types are assembling most actively today? How can we study the ongoing accretion events? Can we constrain past accretion events? And how does it look? How does all of this compare to our expectations from lambda CDM? So the first thing to do, and this is what we've been doing in the SAGES group, is you've got to think big. And the reason you want to think big is, even though the half-light radius, the effective radius gives you half of the light, it gives you less than 10% of the total mass and the angular momentum. So this is just to give you an idea of where things stand with traditional integrated spectroscopy. This logo here is the size of the Sauron field. And the Sauron survey, as most of you know, has been a survey conducted for a number of nearby galaxies. It grew into the Atlas 3D survey, where a large number of galaxies have been observed with two-dimensional spectroscopy. So you've got velocity maps and you've got chemical maps, chemical element abundance maps, but only of the inner regions of the galaxies. And those surveys have been tremendously influential in understanding galaxies and classifying galaxies, but they're only seeing a small part of this bigger picture. And this bigger picture is very important if you want to understand particularly galaxy halo development. So that was our original rationale for the Slug Survey. So the Slug Survey is the SAGES Legacy Unifying Globular Clusters and Galaxies Survey, and we do spend quite a bit of time coming up with these acronyms. So the Slug Survey gives us chemodynamics for 26 nearby early type galaxies with a range of properties, and we've tried to properly sample different property bins. And we do photometry with the Subaru telescope, and we do follow-up spectroscopy with Keck, primarily with the DEIMOS spectrograph. And with these tools, we study the globular clusters out to 10 effective radii, and we get the starlight, two-dimensional starlight maps out to 3 or 4 effective radii. And what I'm going to do in the next part of my talk is just give you some science highlights, the newest science developments, and just to give you a flavor of the different kinds of things we're doing with these data. So the first thing that happened when we started looking at large radii, I should show you, this is one of our velocity maps. This small part in the middle is the Sauron field, and we're able to make sure that our data over the wider field actually runs seamlessly into the Sauron data in the center. So the first thing that we found when we looked at our first few galaxies was that the inner profiles do not predict the large radius behavior. This is a V over sigma against galactocentric radius plot. All of these galaxies, these 4 galaxies, would have been classified as fast rotators in the Sauron survey. And as you go to larger radii, you can see it's all over the place. So that was a strong endorsement of our claim that we needed to go to large radius to really understand how galaxies are assembled. The other thing that we can do is to use our globular cluster and starlight data to compare to cosmological simulations. And I like to call these things wild disks, and I know that Avishai doesn't like that. He prefers the VDI, so I put that in for Avishai, but I like wild disks. So these are the turbulent disks that are observed and are also seen in the cosmological simulations that Avishai and his group work on. And these are turbulent disks at a redshift of 2 or so that are fed by flows from the cosmic web, cold flows from the cosmic web. The disks become unstable, they clump. The clumps migrate towards the center where they build up what looks very much like a classical bulge. So we got interested in this because it's been suggested by Reinhard Genzel and his group, for instance, that these clumps may be the sites of young globular cluster formations. So proto-globular clusters may form in these disks. And inspired by that, we've, and I should mention that these disks, these wild disks at a redshift of 2, are allowed to evolve passively to the present, where they may become, for instance, S0 galaxies, or you're allowed to merge them to make other kinds of galaxies. So again, early in the history of slugs, Jacob Arnold, who's my graduate student here in Santa Cruz and who you'll hear from later in the week on Thursday afternoon, he did an initial case study of the nearby S0 galaxy NGC 3115. So NGC 3115 is a lenticular galaxy at about 9 megaparsecs. And this is a velocity versus galactocentric radius plot where the dark blue points here are the globular cluster, metal-rich globular clusters actually, and starlight data. So that's data. And the teal sort of blue curve here is the curve from the cosmological simulations of Severino et al. So these are Avishai's VDIs. And here, just for fun, is a merger simulation. This happens to be a 3-to-1 merger. But you can mess about with all different kinds of mergers. Here's a 1-to-10 merger. And it's, of course, extraordinarily difficult to reproduce this trend of falling velocity as a function of galactocentric radius with any kind of reasonable merger model, because mergers, throwing angular momentum out to large radius, you'd expect the velocities to be rising. So to reproduce the rapid inner rotation and the low outer rotation is extremely difficult with with any kind of merger model. So this is just to show you how well the cosmological simulations do. Here's the data up here. This is Jacob's data for NGC 3115. This is just a velocity map. And here's the inner effective radius, that ellipse there. And this is a cosmological simulation, just one of them. But this also shows the declining velocity at large radius. And so the idea here is that you've accreted the outer regions by bunch of minor mergers over time, and the inner regions may be produced by these migrations in the unstable disks. So when we look at a larger sample of galaxies, and we're able to confine ourselves to virtually edge-on systems, so we don't have to worry about projection effects or correcting for the viewing angle, things start to fall into place. And we start to see that there's a general result here of declining velocity as a function of galactocentric radius. And you see, you've got to get out to well beyond 1 or 2 effective radii before you can start to see these trends. And over here again, just to remind you, this is actually V over sigma against R. The cosmological simulations show trends that are very similar to the data, whereas the merger simulations are quite different. So I'm not going to say any more about that, because Jacob Arnold's going to be talking on Thursday afternoon. He's going to show you a lot of our data with the two-dimensional velocity maps. He'll explain the techniques, and he'll confront these maps with merger simulations and with the cosmological simulations. So please don't miss that talk on Thursday afternoon. So another thing we can do with our slugs data is we can test this idea that the brightest cluster galaxies are the extreme late assemblers. And here's a picture of a bright cluster galaxy. It's M87. And even in very deep imaging, a galaxy like M87 looks very passive, completely quiescent, except that there's a one stream that you can see, a filament that does actually show up in the image, in a deep image. Otherwise, it looks like nothing at all is going on. When you look at the globular cluster system of M87, the story can be quite different. What we've done with the Slug Survey is we've got over 500 globular cluster spectra, and the spectra are very high precision. They're roughly 15 kilometers a second accuracy, and that compares to all the earlier work, which was nearly an order of magnitude less precise, 110 kilometers a second accuracy or so. So we have very high precision velocities for a very large number of globular clusters around M87. So what looks like a completely quiescent galaxy in imaging is very difficult, very different if you look in the velocity position phase space. So this is velocity as a function of galactocentric radius. And what you start to see with this large number of globular clusters is you start to see these chevron shapes. So there's chevrons here, and here's a filament. That filament actually corresponds to filament. I don't know if you can see it. You can probably see it a bit better in this deep image. But these other features are not observable directly. You need to have the velocity information. And just down here I've put a sort of standard simulation that shows that chevrons like this are a classic signature of a satellite coming in, passing through the center of the galaxy potential, stopping, reversing, coming back out again. So these shapes are a classic signature of satellite accretion. And when you look at these globular clusters that are associated with the chevron in more detail and do the analysis, the number of globular clusters that we infer are associated with this satellite accretion, this shell, in velocity position phase space and the coldness of the shell tell us that it's roughly a half L-star galaxy that has been accreted by M87 in the last gigayear or so. So the thing is, these features are relatively short-lived. They only live for a few 100 million years. So this is a recent accretion event. And it tells us that M87 is in active formation now. And of course, supports the idea of these brightest cluster galaxies being the most recent assemblers. This is some work that was led by Aaron Romanowski. Okay. So the last few minutes, I want to talk about two little cool things that try to show the range of different problems that we're able to address with these data. So one kind of cool little topic is the possibility of constraining cosmic reionization using metal-poor globular clusters. So we're all familiar with the idea, this happens to be from a simulation by Jörg Demand, but the idea is that the dark matter halos sitting on top of the largest overdensities are the ones that collapse first. And those are the ones that wind up concentrated towards the center of the massive galaxies today. So for a variety of reasons, we think metal-poor globular clusters trace those early dark matter halos. So they were formed within those early dark matter halos. And we also think that there was some mechanism which truncated globular cluster formation temporarily at high redshift. And one possibility for that mechanism is cosmic reionization. So consequently, if that's true, then the distribution of metal-poor globular clusters around galaxies gives you an indicator of the epoch of reionization, and looking from galaxy to galaxy, you can see how homogeneous or otherwise that reionization might have been. So this is some work led by Lee Spitler, where we looked at the distribution of globular clusters around the Milky Way, NGC 1407, which is a massive elliptical galaxy in a group environment, and M87, which is obviously in a high-density environment in a rich cluster of galaxies. So this is projected density against galactocentric radius, and you can compare the distribution of the metal-poor globular clusters with the predictions from the distribution of dark matter halos. So the upshot here is, and this was from an idea suggested by Pierre Amadou, Ben Moore, and Jörg Demand some years ago. But the interesting thing is you take the mean constraint from those different galaxies that we've been able to study so far, and it's almost identical to the constraint you get from the cosmic microwave background. But interestingly, there's a density dependence on this result. So there's a trend from low density to high density environments here. And I think the way to look at this is that this measures when reionization ended. So it ended most recently in the high density environments, but it can also have started earlier in those high density environments. But there does seem to be an environmental dependence. So in the last couple of minutes, I'm just going to tell you about one other cool thing that I think, as a collection of observers and theorists, we ought to be aware of, and that is the situation, the changing situation with regard to ultra-compact dwarfs. So we've done a study, as you know, and this is a spin-off, actually. This is a serendipitous discovery, doing our observations of M87 and the globular cluster system. If you look at that corner of M87 up there and you blow it up, you find that there's not only globular clusters, which we've been studying, there's one, but there are also these much larger fuzzy-looking things called UCDs, ultra-compact dwarfs. Now, this class of objects was discovered about a decade or so ago, and ever since the discovery, there's been a debate about whether they're large star clusters, so big fuzzy star clusters, or stripped dwarf elliptical galaxies, so the nuclei of stripped dwarf elliptical galaxies. And we've discovered a large number of them in M87. Now, this is half-light radius, so this is the size of the individual objects against luminosity. And these are globular clusters. This sequence is the globular cluster sequence along here. The darker points are the ones we have spectra for. And the green points here are the UCDs, the ultra-compact dwarfs, that were known before. And it was thought that there was a size-luminosity relation for these objects, which was used as a diagnostic to their origins. Well, what we were able to do was to push to fainter magnitudes than had ever been done before, and we found a new class of UCDs, these faint ones that had not been detected anywhere else, and clearly eliminated this size-luminosity relation. Now, the reason I mention this to you in this group is that there's a lot of these things. So there's about 100 UCDs out to about 200 kiloparsecs in M87. If you look at this everything plot, this is I like this everything plot. It's half-light radius against absolute magnitude. Giant ellipticals up here, compact ellipticals, dwarf spheroidals go along here. Here's that sequence of globular clusters I told you about. And up here are the faint fuzzes and the extended clusters that have been discovered over very recent years. Here's the UCDs, and we're pushing in this away. And we'd like to know whether that's a real gap or not, incidentally. But for reasons I don't have time to tell you about, because I'm done, for reasons I don't have time to tell you about, we think the majority of the UCDs are actually stripped galaxies. So I mention this only because if you sort of make an informed guess about where these UCDs should lie, when you look at the cumulative number of halos, this is from an old plot by Ben Moore and collaborators against VC over V global, it could be a very significant factor in cosmic accounting. So we don't know whether UCDs have dark matter now. We'd like to know that. So it's unclear how to assign UCDs to dark matter halos, but it may be a very significant factor. So I just summarize. I've introduced the Slug Survey. We're looking at globular clusters to 10 effective radii, stars to 3 to 4. We're able to test two-phase galaxy assembly. We're finding that halos are built up by minor mergers, that major mergers are inconsistent with this rapid inner and low outer rotation, and we like these cosmological simulations of wild disks or VDIs. That they seem to agree very well with the data. We found this enormous shell in velocity position phase space in M87, so we can actually detect the kind of substructure in galaxy halos that you can only do in the local group if you're confined to field stars. So with globular clusters, you can push that whole analysis much further out. We have some fun constraints on cosmic reionization, and we need to think about UCDs in terms of the cosmic accounting. Okay, thank you. I'm sorry. We don't have any UCDs in the Milky Way.
I like your name, wild.
Yeah, me.
I would say it's a wild massive disk. If you do ordination, don't use it in the airport.
See, Avishai, Anatoly likes wild discs too. I think we should have a vote.
How did you avoid picking these new class wild disks with one criteria?
So what we were doing was we were just taking every, we were doing color and magnitude cuts. Color and magnitude cuts, and then so we were taking velocity measurements of everything that fell in the right cut within the globular cluster cuts, and then we followed up with looking at the HST archive to establish the sizes of these things, and we found that we were finding really faint things that were big and were not formally classified or actually formally detected as ultra-compact dwarfs.